name's Peter. I work in the ST landing team, and I know this is billed as a core development presentation, but Ryan let me kindly put it on the toolchain tract. And today we'll be talking about Linux kernel awareness. So the theme of this Connect is engineers and devices working together, and I would say we want them, how do we want engineers and devices to work together? Well, ideally we want them working together efficiently with good tools. And of course we can buy expensive proprietary tools, but ideally we would like to be working together with good free and open source tools. And that's kind of where this presentation is coming from, really, on how we can sort of enhance GDB to make it better for certain types of debugging. So, overview of the presentation, the rationale for kernel awareness in GDB, going to look briefly at various ways you can debug the Linux kernel with GDB, sort of what the problem is, so what you get today if you use upstream GDB to debug the Linux kernel, what the landing team's doing in this area, what we actually mean by Linux awareness, and the approach that we've taken so far, the progress we've made. We've got a short little demo that I can show you, and then we can also look at some of the alternative approaches that we could have taken, and it'll be obviously good to get people's feedback and opinions on it. So the rationale is many of us need to debug the kernel. Proprietary tools such as Trace32 and DS5 are very expensive. And the open source debuggers like GDB lack some of the kernel awareness features that you find in these tools. So one of our missions is to, landing team missions, is to try and make the debugging experience a bit better when you use upstream GDB to debug the Linux kernel via JTAG or QEMU. So what ways can we debug the kernel with GDB? Well, you can have the GDB client connecting to a GDB remote stub, and there's KGDB, which is we'll briefly touch on, but mainly what this presentation is about is B and C, where we're using QEMU or connecting to a OpenACD GDB stub for JTAG debugging. You've also got core dumps that we'll briefly mention, but that's really just to make you aware of another potential use case and work going on in this area. Yes, KDump and a crash utility. But that's not our primary use case. So KGDB with GDB, you turn on the config KGDB kconfig symbol. The advantages are it's already supported on many platforms, and all the kernel threads are correctly enumerated in GDB, which is something that we're going to talk a bit about in this presentation. But it quite often isn't enabled on production systems, and it requires a certain amount of workingness of the target for the stub to be alive, and it also isn't that good for early sort of hardware bring up, because you need a certain amount of support already running on your kernel to get it going. We've also got QEMU and GDB. Now this is a really good development environment, especially if you want to test generic kernel code on different architectures quite quickly. It's also very good for developing Linux awareness extensions, because you can quickly boot it on ARM or an x86 kernel and see if it works. But of course, if one of the main reasons for JTAG is it's really useful for SOC and board bring up, and if your problem is in that area, QEMU is unlikely to be particularly useful for you. but it does have a GDB remote stub that you can connect to, which is quite cool. And that's a quick example. So the top, you probably can't read that back there, but the top window is booting the kernel, bottom window is GDB, connecting to the stub in QEMU, and then you can sort of do some debugging. And then we've got what we call external debug, or JTAG, or serial wire debug. And this is, in this presentation at least, we're going to be talking about OpenOCD, which is an open source project that gives you essentially two interfaces: a telnet interface, which allows you to issue JTAG commands to the target, and a GDB remote interface that allows you to connect GDB to OpenOCD, and then it has JTAG down to the system that you're debugging. It's open source, supports many FTDI-based JTAG probes that are often very cheap, so only sort of $30 or $40. And it provides a pretty powerful debugging solution. So why external debug? Well, it allows access to the dedicated SOC debug hardware externally. You can access the flow control using hardware watch points and breakpoints on the SOC. It's really a tool that allows you to debug in situations where other mechanisms may not work, like interrupt handlers and from the reset vector when you turn on the board, loading code directly into RAM on a blank board, and scenarios like that. So when combined with GDB, it can be quite powerful. We'll skip over that because we've got a demo later on. So this is kind of maybe my own sort of view of where those tools sit on a kind of line of good to better, but it's a little subjective on exactly the thing that you're trying to debug. This is more if it was a kind of SOC or board related issue. And where core dumps come in, I'm not quite sure. The enterprise guys sort of use core dumps quite a lot. And then we've got core dumps. So we'll briefly touch on it. It's really, you can debug the kernel using prop kcore, and also Red Hat have a series of utilities called crash, which is it's kind of like a mashup of GDB and an old utility called crash that allows you to, if your kernel's crashed, you can k-dump it out and then load the dump file into this crash utility and debug it and get threads and whatnot. Have you got a question?
No, is this on? Just a comment. I've used in the past crash on a PCI adapter running, there was a PowerPC SoC to look at the kernel running in the host system that the PCI card is plugged in. That was also really useful.
Okay, well, that's good to know. So in this same vein, like crash sort of gives you some of these similar kernel awareness sort of stuff in that you get the kernel task list and things. There's also a project called GDB-kdump, which is some guys at SUSE which are trying to merge that kdump function, like basically merge that functionality into GDB properly rather than having this separate utility. And they've also developed this libkdump file library that supports loads of different crash dump file types. And then PyCrash, we briefly touch on later, is almost an attempt to do that same thing, but using Python extensions rather than a C plugin. So what's... Sorry? I've not heard of LCrash.
So LCrash came out of SGI originally and then was used by IBM on the mainframes and other architectures.
Okay.
It was supported by user at the time when Red Hat came up with Crash, and it's similar to Crash, but it's a different implementation of the same things.
Right, okay.
Started out with a fork of GDB, really old GDB.
Right, okay. Yeah, I mean, this is kind of what we're trying to do now is, as you'll see later on, is upstream some of this stuff to GDB rather than having all these different utilities that are kind of forks of GDB or, you know. So today, what's the problem? Well, if you connect GDB to a kernel that you're debugging in either QEMU or JTAG, it can be a bit disappointing compared to commercial tools, or in fact STGDB, which has these extensions. So if you do an info threads, what you get is it will show you the thread running on the physical CPUs. So if you've got a dual core system, it would appear as 2 threads. If you've got a single core system, it would appear as 1 thread. And there's no visibility of the other sleeping threads in the system, and there's no visibility of the user processes. If you backtrace, if you happen to have halted the kernel whilst you are in the kernel, you'll be able to backtrace that CPU back to the kernel user boundary. But if you, that's actually the next slide, I think. But if you happen to hit it whilst it was in user space, you'll just get what the example trace on the right-hand side there, where it's not understanding the virtual addresses. And then the other sort of GDB context commands like up, down, frame, number, thread number, they're all the same. So thread number would switch the physical CPUs. Up, down is going to take you up the stack frame of the physical CPU as well. And this could be much better, more like what KGDB does, where you get all the kernel threads, or other sort of proprietary tools. So what are we talking about with Linux awareness? Well, I'm sort of splitting it into 3 areas of task awareness, which is allowing GDB to be able to see all the threads in the system and be able to switch between them with the context commands like thread, number, etc. And then we've got loadable module support, which is GDB correctly being able to detect modules being loaded into the kernel and pull in the symbol information for them. And the third one is OS helper commands. So that's basically extra little commands that can extract some interesting state for you from the operating system, which you could do manually, but you don't want, it's just helpful to have a command to help you do that. So the landing team, ST landing team, what we're doing in this area is ST had a JTAG debugger called the STMC2, which is on the silver box on the right-hand side. And that worked with a GDB plugin called Linux Kernel Debugger, which was LKD for short. And this does a lot of those features we talked about on the previous slide. And what we're trying to do is extract and rework those features and upstream them to either GDB or the kernel, and slowly reduce the outer tree patch set. We've been sort of coming up with an approach on how to do that, which we'll talk about in a moment. But also, another part of it is trying to sort of let people in the community in Linaro know what we're doing, so other people may have interest, which is one of the reasons for this presentation. We've also done a couple of presentations at ELC.
This piece of hardware there, have you also added support for OpenOCD to use that thing as backend for your JTagging?
No, we haven't. Everything we've been doing, we're trying to stick with JTAG adapters that are freely available and already supported. But that JTAG, we could do that, but we haven't. We're trying to stick with just completely open solutions. So it's a quick overview of the patch set. It's about 14,000 lines of code, and it's all sort of self-contained, and there are separate files to the rest of GDB. So it needs, to get it upstreamed, it needs quite a lot of reworking and sort of breaking down into sort of small bite-sized chunks. So we have this kind of question on where we want to put the awareness. We could put it in the GDB client, which is where LKD sits, which is a C plugin. Equally, we've also got, you can extend GDB with Python, so we could put some of the awareness in Python, or we could take the approach that KGDB does and put some of the awareness in the stub, and then that doesn't require any sort of changes in GDB. Now, extending with Python, there's quite a few Python bindings in GDB that allow you to add extra functionality, so custom commands and frame filters and helper functions. And this is quite useful for the Linux awareness because it allows us to put the Python code in the kernel source tree, and then it avoids this cross-dependency between the kernel and GDB. And the idea is that you will always, when you check out your kernel release, you should have Python scripts that match up with the kernel code that you're trying to debug. This sort of route was established by this guy Jan from Siemens. Jan from Siemens. He's merged several scripts already. You can see at the following links there: GDB kernel debugging, text file, and you enable config GDB scripts, kconfig symbol. You also need to add into your GDB init file. It's okay to execute these scripts. And you get a series of extra commands then. So in 4.6 kernel, you can see in bold the various extra commands that you now have in GDB. One of the most useful is LAS16-message, which extracts the kernel log buffer. And some of these commands, like dmessage, we had a C implementation of it in LKD, and we've been able to kind of retire the C-based parts and migrate stuff over into Python. So what's the landing team been doing? Well, like I was just saying, we've been trying to take, so some commands that were implemented in LKD, there were already Python implementations of. Some of the other commands where we had C implementations, we've been trying to migrate them into Python and then merge into the kernel. So the first two are LX command line and LX version, which, as you can imagine, are quite simple commands. But the slightly more useful one is the LXIOMem. That they're basically the same as extracting state from the proc file system, but they're useful in as much as if your kernel's not booting and you have JTAG enabled, you can reach in and extract this state. So IOMem will show you, what devices have IO remapped to what memory, and you may get some sort of hint as to kind of what's gone wrong. So there's some example output of those Python commands. There's the LXIOMem one. And these ones were merged by the landing team, and then we've retired that code from LKD. FDT dump. This is something that we've not upstreamed yet, but it extracts it dumps out the device tree to a file.
Is this the original device tree, or do you reconstruct the GDB from the device tree?
This is the original device tree, so the initial boot params one. So I think the main use for this command is, I've had this before where uboot goes and rewrites some stuff in your device tree, and then your kernel doesn't boot, and you don't really quite know what it did. So the idea of this is you can just dump that initial device tree out to on your host via JTAG, and then you can use standard sort of tools to do further processing of it. So on the thread awareness, there's a couple of approaches we could take, and the approach we've decided on at the moment is to extract a minimal C-based patch set for kernel threads, which we're calling Linux K-thread. posted a RFC, but that was kind of a much bigger patch set back in February, and it was still very much in the same layout and structure as the original LKD code. But we didn't receive much feedback on the mailing list, but we have been working with Yao, who's a ARM toolchain GDB maintainer and assignee to the toolchain working group, and we've been sort of reworking that patch set to fix style issues and all the sort of things that you'd expect, really, that need to be sort of sorted out before it's really acceptable to get pushed upstream. And what we have is the patch is sort of working well with NoMMU, Linux, OpenOCD, and GDB, and we've got a little demo of that. Oh, I've jumped the gun. That's about the size of the patch set, so we're looking about 1,500 lines of code at the moment. And this is a diagram, basically, showing that sort of debug architecture that I've just described. So in the grey box, you've got the software components. So we've got Python plugins living in the kernel source, which are extending GDB, and then in GDB, we've got a C plugin called Linux K-thread, and then GDB can be connecting to QEMU stub or an OpenOCD stub, and in the case of OpenOCD, you'd then be connecting to real hardware over the JTAG probe and your target. So that's how we're hoping to sort of implement the awareness. So now we've got a quick demo. It's just demoing that patch set with the Python commands and JTAG. It's on, I'm demoing it on a NoMMU part because that makes things a bit simpler in terms of virtual memory and not needing to worry about it. But it correctly shows that we're enumerating the kernel threads in GDB and that end-to-end system sort of working together. Oh.
Yep. What's the current state of the mainline GDB? Is it what kind of architectures does it support? And do you support V7? V7. Yeah. Just V7.
Let's put it there. So, yeah, let's go. So we don't really need to worry about that one. Because that's just the JTAG, and it's detected that we've got 6 breakpoints, watch points. So that's OpenOCD connected. This window here is the kernel console. Missing a terminal. Ah, no. Okay. So this is the telnet interface to OpenOCD. So we're going to resume, and we should see the kernel boot on the right-hand side. Yeah, so that's good. Then we're going to halt the target. So that's halted it by JTAG. And then I don't know if you can see that, right? How well you can see that. So this is GDB with the plugin, the K-thread plugin, and it's connecting to OpenOCD. And then you can see it's detected that we've got these various threads in the system. So like I showed before, usually on a vanilla upstream GDB, you would only have one thread on this single core system. So now if we do an info threads, you can see a slight bug where it's showing at 2, which shouldn't be doing. But this is the physical CPU, and then all these other threads are the sleeping scheduled threads in the system. So you can then use the commands we talked about to switch to the other sleeping threads and get back traces, etc. And at the moment, we're back tracing there back to the source kernel user boundary. So we can, if we set off another process now, so we do sleep. Oh. If I break back into GDB, you can see that it is correctly detected that a new thread's turned up, and we can go and look at that. Thread 22. Backtrace that. Continue. Oh, we got it just in time. If we break in again now on the JTAG, we should see that that thread's now been removed from the thread list, which it has been. So that's kind of the basics of that C plugin. You can also see that we've got the various LX Python commands, so LXI mem. There's not much enabled on this STM32 upstream, but you can see serial and various pin controller devices that have IO remapped memory. And that's it. Just go back to the presentation. So what are the challenges at the moment? Well, there's a reason that the demo's on a NoMMU platform, and that's because we have to handle sort of virtual memory somehow, which we haven't sort of solved that issue yet. The main problem is if we can hold the target at any time, and you could be in user space at that point with a user space mapping. And if that's the case, then you can't read any kernel memory. So we need to be able to detect this situation and either deactivate the plugin, or what LKD does in this situation is reconfigure the MMU for the kernel mapping so you can still read the kernel memory and then put things back to how it was before. So with that in mind, I've done a little bit of prototyping with QEMU, and GDB has this target XML, so you can tell GDB what registers you're supporting via the GDB remote protocol. So I've kind of extended QEMU to also return some of the coprocessor registers, so the TTBR registers. And this seems to work quite well. So with that extension in QEMU, if you then do an info registers, you also get some extra coprocessor registers. And to start off with what we upstream, I think we won't include this, and we will say that we will detect if from the program counter, I think, if we're in, if it's a register that isn't, if it's an address that isn't in the kernel memory, and either print a warning or just deactivate. But what we ideally want to do is, much like LKD, is if you break and you're in user space, to be able to reconfigure the MMU for a kernel mapping and then be able to do what you need to do. And this is my sort of proposal on how we do that, which would be to return coprocessor registers over GDB remote protocol.
Would it make sense to inject some interrupts against the target into kernel space instead?
You could try and do that. So you could, if you detected you were in user space, you could set some sort of breakpoint, I guess, to re-track back, when you know that you're in the kernel. That's something I've not looked at. I mean, with this approach, I would also need to update OpenOCD to sort of make the same change. But at the moment, we're just just sort of prototyping it out to see how well it works, really. I mean, the main advantage of it being returning these registers in the register cache is you can then also access them from Python as well. So you could potentially have a Python script that can read like the ID register and know, oh, I'm executing on this ARM core, or this core that I'm debugging has certain features. So, and at the moment, GDB is quite user space centric, so you don't know particularly what core you're actually debugging on at the time. So the next steps for us, well, we're trying to get this refactored implementation merged. That's going to be the K-thread patch, but quite possibly with some limitations on if you hold, and it happens to be in user space. We need to get some CI set up because we need some automated way of being able to test mainline kernel with this plugin. And then there's a few other commands in LKD that we could migrate into Python, but all of these rely on more virtual memory support. We've got a couple of known bugs where GDB APIs can behave differently sometimes when connected to a QEMU stub, to an OpenOCD stub, and I've not quite figured out yet what bit of software is at fault there. And there's also a bug in the GDB Python layer that I'm hoping I can get someone in the toolchain working group to fix. Other potential extensions. So we need to ideally support x86 and ARM v8. Like we spoke about earlier, there's various other utilities for crash dumps, like crash, and we could look at trying to support that use case as well. An alternative, one of the alternative approaches is to try and do thread awareness all in Python, and we do have some sort of prototype patches for that, but you have to extend a lot more, you have to expose a lot more GDB objects and Python bindings to get something that works, but that's another potential route that could be explored if we can't get our C extension upstreamed. And another quite useful feature of LKD is that it can actually backtrace right back into user space, and that is another feature that once we've got the initial K-thread stuff upstream, we could look at implementing that as well. But that adds in a lot more complexity. And that's it. Is there any questions? No, there's no batteries.
So in the GDB stub, is its awareness of memory entirely flat, or does it have an awareness of the difference between a virtual address and a physical address?
Everything's deals in virtual addresses, basically, in GDB. In the LKD plugin, it does some translation, but that's part of the plugin, really. In OpenOCD, it does have some virtual to physical address translation that you can access using the monitor commands. But yeah, everything is virtual addresses from GDB's point of view. Well, the symbol file you load in is all virtual addresses.
So when you're in user space, how come it can't get the backtrace?
Well, you haven't loaded in any of the symbol files for any of the user space libraries, basically. Yeah, well, the LKD plugin has extensions for doing all that. And you can go off and look for the file system and load in the symbol files. Well, the addresses, the mapping changes. All the kernel virtual addresses are in the VM Linux, and then. Yes. If we we need to add in support to like try and pull in all that debug information from user space and see if we can find the symbols in the root file system. And the LKD plugin does do that, and it can be done. It's just a lot more extra code. And then you need to sort of get rid of it all again when you continue. Oh.
So what versions of Linux you want to support? And I also have a comment about address translation. So can we utilize the OpenOCD based address translation here instead of doing it in the LKD plugin? Or because if we add support there using the kernel data structures and the registers values at that time, then we can virtually read those addresses as the virtual memory addresses, and translation will be automatic in OpenOCD.
I'm trying to avoid putting too much intelligence in the stub, mainly because if you do that, then you have to add it in every stub, so you'd have to have something equivalent in the QEMU stub. And so my preference at the moment is to either have it in the GDB client or in Python, just so you can connect, in theory, to any GDB stub and have this stuff work.
But I don't think that you would be able to sort of do the address translation in GDB client as long as you do it in Python. Then you'll have to keep updating that code as well, because changes will happen, and also there are different sort of architecture variants behave differently for sort of MMUs. Different MMUs are there, so you'll have to keep changing and updating that code as well.
Yeah, for sure. That's one reason for not including this stuff in the initial versions. But as the Linux K-thread stuff does already have architecture-specific bits, because you need to know, what the particular architecture saved on the stack when the thread went to sleep. So there's already architecture-specific parts to it. And what happens at the moment is if the plugin loads and the architecture object doesn't have, support for that architecture, it just disables and you'd never know it was there, basically. Anybody else?
Cheers. You mentioned the problem of being in process context, not having the MMU mappings. There's also idle when we turn the MMU off. Is that being considered at all?
No. Also, what, CPU idle, you mean? Or yeah, CPU idle is also another problem with JTAG debugging generally, because we lose access to the debug hardware as well. So what we found with OpenOCD at the moment, it could be good to talk to some ARM guys, I guess, is when the core gets turned off, we get disconnected from the debug port. So most of the debugging at the moment, we've been turning CPU idle off on that system, just to say the JTAG doesn't keep disconnecting.
And just one other comment, the thing about reconfiguring the MMU to be able to access stuff, probably aware, but it's slightly, doing so is slightly scary because of things like the way we use ACIDs in the kernel. There are potential issues with just changing the mappings behind the kernel's back, which it might be worth just discussing that on the list.
Yeah, no, yeah, definitely. I mean, that is one whole area which is sort of full of problems and needs to be thought about, definitely. I mean, it seems to work fine in the LKD plugin, but I'm sure that could potentially introduce, but whilst upstreaming it, we're now sort of potentially opening ourselves up to many other types of hardware and cores and things. So, yeah, it could become an issue. It'd be good to talk to you a bit about exactly what you think the problems may be. Anybody else?
Could you share that the actual use case of the debugging for each let's say features like functionalities like let's say this function is useful for which situation or something like that?
So I'd say JTAG generally is useful for debugging in situations where the other mechanisms maybe can't be used, because you can single step and use the dedicated debug hardware. I mean, the thread awareness in a previous, when I was at ST, was really useful when you had lots of deadlock type. They had a lot of middleware drivers, so it wasn't really particularly an upstream kernel. It had lots of middleware added in with lots of threads and lots of locking, and you could quite often get a case where everything deadlocked, and being able to easily go around all the different threads and inspect the state within GDB was actually really useful. I mean, I guess that would be the main. There's other tools for doing this stuff, but being able to switch threads and go up and down the stack frame of any thread in the system can be quite useful for accessing, structures in those threads and things to try and figure out, what happened.
I think it's more sophisticated debugging than adding print case and trying to root cause it. You could single step and analyze what's changing in each step, and yeah, you could resolve it in a much more sophisticated way.
So that's for the thread awareness part, which I guess is one of the main things we're trying to add. I mean, the Python stuff is useful in more contexts, because the Python you could be using with a core dump, or you could be using it with QEMU or with JTAG. So, I mean, personally, I've used the Python like to dump the D message, or the device tree has been quite useful if you booted your board and just nothing came out, and you think, what's happened there? And you can extract that state, and again, yeah, there's other ways. There's always many ways to debug a problem, but these are just sort of some of the examples of when I've used those tools. Anybody else? No? Well, thanks all for attending.